Hi, my name is John Amos,
And I'm Joseph McNeil.
And I'm Connor McGowan-Nicholson.
and this is our Chapter 12 video project. In this chapter, we go over three main topics. They include the crystal structure, mechanics of ceramics, and hardness. In the crystal structure, we notice that ceramic bonding ranges from purely ionic to covalent. We also notice that carbon plays an important role in this chapter because it can exist as diamond or graphite. And the last thing in this section is imperfections. Cations and anions are still capable of their own types of imperfections, which include point defects, interstitials, and vacancies. In the next topic, we notice that ceramics are very brittle. This leads to low ductility but very high tensile strength. And also, many ceramic bodies are porous. This means that the modulus of elasticity decreases with volume fraction porosity, and also that the porosity decreases flexural strength. The last topic includes the hardness. It is hard to determine the hardness because of the cracking that occurs in ceramic materials. So now we use microindentation Knoop and Vickers hardness testers that include a pyramidal-shaped indenter. Ceramics are also the hardest known materials, and the majority are used in abrasives. In this slide, we'll talk about the crystal structure. More importantly, Table 12.4, which explains the different types of crystal structures and how many cations and anions make up the structure. For example, the structure name rock salt has a structure type AX, which means that they have the same number of cations for every anion. The anion packing is an FCC structure, and this goes differently for each structure name. The coordination number plays an important part of each of the equations because this is the N prime value. And examples of rock salt include sodium chloride, magnesium oxide, and iron oxide, and this goes the same for each structure name. In this slide, we'll talk about the equations. The first equation is the density of a ceramic material, and this actually is where we use the N prime value. The flexural strength for a bar specimen having a rectangular cross-section is the next equation that we use in this chapter. The next equation is flexural strength for a bar specimen having a circular cross-section. Next up is the elastic modulus of a porous ceramic. And last but not least, the last equation is the flexural strength of a porous ceramic. This chapter focuses on many different ways to test the mechanical strength of ceramics. The best way to test for flexural strength is a three-point loading scheme where you have a point load in the center of the beam with two supports on each end. We notice that ceramics have very low flexural strength, they're very brittle, but they have a very high tensile strength. Another topic this chapter talks about is the cation-anion radius ratio. The coordination geometry number determines the cation-anion radius ratio, and this figure shows the different types of ratios that correspond to different geometries.
Here we have question 12.29 as an example. And in this question, we're supposed to calculate the fraction of lattice that are Schottky defects for cesium chloride at its melting temperature, which is 645 degrees Celsius. And we're supposed to assume an energy defect formation of 1.6 electron volts. Alright, so in order to solve this question, we need to use the equation that the number of Schottky defects is equal to the number of lattice times E raised to the negative activation energy of a Schottky site divided by 2 times the Boltzmann constant times the temperature. So in this problem, we're given everything here except for N. So to solve for N is equal to Avogadro's number times the density divided by the atomic weight of the atoms that make up the cesium chloride. So Avogadro's number is 6.022 times 10 to the 23rd atoms per mole, and the density is 3.99 grams per centimeter cubed. And then we multiply that by 10 to the 6 centimeters cubed per meter cubed in order to get grams per meter cubed. So we can determine that N is equal to 1.43 times 10 to the 23rd lattice per meters cubed. Alright, so using the equation from above, now that we know the number of lattice, we can multiply that by E raised to negative 1.86 electron volts, and then divide that by 2 times 8.62 times 10 to the negative 5th, and then 645 plus 273. So then we determine that the number of Schottky defects is 1.12 times 10 to the 23rd defects per meter cubed. And so to find the fraction of Schottky defects, we just divide that number by the number of lattice, and that fraction ends up being 7.85 times 10 to the negative 6th.
Alright, question 12.26. The problem statement for this question is, compute the theoretical density of zinc sulfide given that the Zn to S distance and bond angle are 0.234 nanometers and 109.5 degrees respectively. How does this value compare with the measured density? The equation we're going to use to solve this problem is rho equals n prime times the sum of the atomic weights of the cations plus the sum of the atomic weights of the anions divided by the unit cell volume times Avogadro's number. Alright, so we can say that Avogadro's number is 6.022 times 10 to the 23rd. The sum of the atomic weights of the cations is just zinc, because that's the only cation in the equation, and its atomic weight is 65.38 grams per mole. And the sum of the atomic weights of the anions is just the atomic weight of sulfur, which is 32.07 grams per mole. Next, we need to find n prime, and we can see from table 12.4 that the number of formula units in the unit cell, which is what n prime is 4. The only variable we need to find now is Vc, which we can calculate using what we know about zinc and sulfur. Alright, so we know the zinc to sulfur distance is 0.234 nanometers, and the bond angle is 109.5 degrees. We can use this to create a triangle from one of the zinc atoms to the sulfur atoms, with the hypotenuse being 0.234, the height being x. We can determine by just looking at the structure of the zinc sulfur cell, and we can see that that is the 1/4 the side length, and theta, which is our angle, would be 90 minus phi, and which we can tell from the book that phi equals the bond angle divided by 2. So using trigonometry, we can find that x equals 0.234 times the sine of theta, and from that we can say that a equals 4 times 0.234 times the sine of theta, which ends up being 0.540208 nanometers. Alright, we can find from the tables that the experimental value for the density of zinc sulfide is 4.10 grams per centimeter cubed. Okay, with that in mind, now we can calculate the theoretical density. So first we need to define our Vc value, which is a cubed, which ends up being 0.157646 nanometers cubed, or 1.57646 times 10 to the negative second centimeters cubed. So now plugging in all of our values, we get that the theoretical density of zinc sulfide is 4.106 grams per centimeter cubed. We can say that the theoretical density that we gained through calculation is relatively close to the measured density of zinc sulfide. Thank you.